Stanford University.
All right, I want to discuss, again, we did do the ideal gas, did we not? Yes. The ideal gas of point particles. Now, I want to talk about the ideal gas of particles which are not point particles. Under what circumstances is a gas well approximated by an ideal gas? An ideal gas is one where particles don't collide with each other. And the answer is when the density of the gas is low enough. And it doesn't matter very much if the particles themselves have some size and some structure, as long as the distance between particles is much, much larger than the structure of the particle itself, it's still an ideal gas. So particles, in this, particles, molecules, and so forth, molecules certainly have structure. They can rotate, they can vibrate, but this leads to a very big paradox in classical statistical mechanics, and there's one that was only resolved by quantum mechanics. It was considered one of the big paradoxes about classical, statistical mechanics at the end of the 19th century. And as I said, it only got resolved by the same ideas that resolved the problem, essentially almost exactly the same ideas, which resolved the big problem about black body radiation, which we will come to. So if you don't know what the problem of black body radiation is, don't worry about it right now. The problem of molecules had a very, very similar flavor to it. And let me tell you what the problem of molecules is, and we'll do it by doing an example, a molecule with structure. Now, this is a very, very simplified version of the structure of a molecule. But it's enough to see what the problem is. Let's replace the point molecule, oh darn it, let's replace the point molecule by a pair of atoms which are connected by a rigid rod. Now, in the notes that are on the internet, which are available to you, I did the problem explicitly of a molecule built like this, which is free to rotate around in 3 dimensions. I'm going to simplify it here because all of the essence of it is in a simpler story. Namely, the molecule is only free to rotate in a plane. All right? So the molecule is free to rotate around an axis, and the axis could be one of the atoms. A simple example would be that there's a heavy atom and a light atom. The heavier atom will tend not to move around so much, and the light atom will revolve around it at the end of this entirely rigid rod. Okay. The atom has, in addition to the usual kinetic energy of motion, overall motion, it has an additional energy of rotation. And that additional energy of rotation can be excited, for example, by collisions between 2 such molecules. 2 such molecules come together and they hit each other off center, and even if they weren't rotating, after they hit each other, they will start rotating. So the rotational energy is part of the energy, and it has to be accounted for in studying the statistical mechanics and the energetics of this gas of these molecules. Okay, so let's first consider the energy of rotation. And as I said, for simplicity, this is purely for simplicity, let's take one of the atoms to be heavy enough that it moves with a much lower velocity than the other one. Really, of course, the complex system rotates about its center of mass. But if one of the atoms is heavy, then the center of mass is close to that atom. It's like the solar system. The solar system revolves around the sun. Well, not quite. The Earth doesn't quite revolve around the sun. The sun and the Earth revolve around the point, which is the center of mass of the sun and the Earth, assuming we didn't have to worry about Jupiter. but it's not such a bad approximation to put the sun at the center and say the Earth moves around it. And in that case, you can ignore the motion of the central one, the heavy one, and the kinetic energy involved is just the kinetic energy of the light one moving around. Okay? This is not essential. This is in no way essential to the story. Okay, so what is the energy of such a molecule? Well, first of all, there's a translational degree of freedom of the molecule. That just means the motion of the center of mass. Okay? And its energy is exactly what you would expect. It's the total momentum squared divided by twice the total mass of the molecule. I'll use capital M to indicate the total mass of the composite molecule. And that's one of the terms in the energy. And there's, of course, a term like that for each molecule, so there's really a summation sign, which I won't bother writing out. And then there's the rotational energy. So for the rotational energy, let's just imagine the center of mass is at one of these molecules, and the other one gets to move in a circle. It gets to move in a circle, and let's take the radius of the molecule to be small r. Okay? So what is the kinetic energy? Let's take the light atom and make its mass little m. And of course, the kinetic energy of rotation is nothing but the kinetic energy of moving around in the circle. It's just m times the angular velocity, not the angular velocity, but the tangential velocity, let's call it v squared, divided by 2. This is not the overall velocity. This is the component of the velocity if we pretended that the center of mass was standing still. So it's the velocity around it, the circular velocity, and that's it. That's the kinetic energy. Let me rewrite that. The velocity moving around in the circle is proportional to the angular velocity. So let's call the angular velocity theta dot, the time derivative of the angle, the angular orientation of the molecule. Theta dot times what? R. Theta dot times R. And we can plug this in here, and this gives us mr squared. And r now is not a dynamical variable. It's the fixed length of the rigid rod connecting the two atoms. It's, of course, associated with the rigidity of certain molecular bonds. Sometimes molecular bonds are pretty rigid, and this would be an instance in which the molecular bond was very, very rigid and didn't allow much inward-outward motion. All right, so this becomes mr squared over 2 times theta dot squared. Now, mr squared is just a constant and it has a name. It's the moment of inertia. So we can give it a name, and it's usually called I divided by 2 times theta dot squared. And for our purposes, the definition of the moment of inertia is nothing but mr squared. It's just a symbol that I use to simplify the formula. I over 2 times theta dot squared. Now theta dot, or theta, excuse me, is a generalized coordinate. If we go back to our studies of mechanics, we remember that we can think of any possible description of the coordinates of a system as being more or less on an equal footing and work either with position along here, or we can work with angle and apply the standard rules of classical mechanics. The standard rules of classical mechanics involve, among other things, constructing a Hamiltonian, which constructing momenta, which are conjugate to the coordinates. The coordinate in this case is theta, and the momentum conjugate to it is called angular momentum. All right, what is the rule? Incidentally, this is the kinetic energy. It's also the Lagrangian, for those who like Lagrangians. This happens to be the Lagrangian of the circular motion. So think of it that way. What is the definition of the momentum conjugate to theta? Anybody remember the definition of conjugate momentum? The derivative of the Lagrangian with respect to the time derivative of the coordinate. All right? So that just means the derivative of the Lagrangian with respect to theta dot. So the angular momentum, now I had a reason for not writing that this is equal to L the Lagrangian, because the standard symbol for angular momentum is also L. Sorry about that. The L that I'm writing here is not the Lagrangian, it is the angular momentum, standard symbol, and it's equal to the derivative of this object with respect to theta dot. Just as, well, you know the story, I don't have to tell you. So the angular momentum is just I theta dot. Now, again, this is not Lagrangian. Oh, I suppose I could write this as scripty L for Lagrangian. This is angular momentum, and it's I times theta dot. Let's now rewrite the kinetic energy in terms of angular momentum instead of theta dot. Here we have it in terms of theta dot. Easy enough. We just solve for theta dot in terms of I and L and plug it back in. What do we get for the kinetic energy? We get the extra term in the kinetic energy is L squared over twice the moment of inertia. When we square theta dot, we get L squared over I squared. Well, there's an I in the numerator here, I squared in the denominator, we get 1 over I. So L squared over I. And this becomes now the energy of a molecule in terms of its linear momentum. That's this. There are 3 components of it, just as there would be for a point particle, and 1 additional momentum, namely the angular momentum. This is the expression for the energy. The new thing now, though, from the point of view of statistical mechanics, is that a configuration involves the position, the overall center of mass position, the momentum, and also the angular momentum and also the angular coordinates. Okay, here's a rule, and I think you probably discovered this by yourself by now, that whenever the energy consists of 2 terms that are independent of each other with no interaction between them, and here there's no interaction between the rotational motion and the translational motion. There's nothing, for example, in this expression which links these 2 terms together. Rotation can happen independently of translational motion, nothing to link them together. When you have a situation where there are 2 completely independent degrees of freedom, the partition function factorizes. In other words, let's first write out the partition function for a single particle. Let's put a single molecule in, all right, at a certain temperature. Then the partition function for that single molecule is the sum, or the integral, the sum over all the configurations. All right, I won't write that yet, but let's write e to the minus beta. And now we have the usual, let's write it, p squared over twice the mass. That's it, right? Yep. And then plus L squared over 2I, but let's just write that as a product. E to the minus beta, L squared over 2I. We have to sum this over all the configurations of the particle. That means, first of all, integrating over the center of mass location of the atom. That's exactly the usual d cubed x. We have to integrate over the momentum of the linear momentum of the particle. That's the usual d cubed p. But now there are new coordinates that we have to integrate over, namely the position of the molecule along the circle and its angular momentum. Just as we integrated over position and momentum here, we have to integrate over angular position and angular momentum. So we might as well write down another integral here, d theta dl. And that's it. That's the partition function for a single particle. What would the partition function be for n particles? Well, it would be a multiple integral of a similar kind, but we've already learned from experience that when you have n particles, it's just the nth power of the partition function for one particle. So later on, we can remember that we should take the nth power of this, capital N, where n is the number of particles. This is the central thing that we have to be able to compute. Okay, first of all, the integral over the position, that's, as always, the volume to the nth power. Let's throw in our friend, the 1 over n factorial, which I forgot to put into this formula here, and I don't have enough room anymore. Yeah, we can put it in. 1 over n factorial. The usual 1 over n factorial for identity of particles. Okay. Volume to the nth comes, or yeah, we're only doing it for one particle, so let's just do it for one particle. Volume, period. We'll come back to the multiple. Volume from d cubed x. Now, do you remember what we got by integrating e to the minus beta p squared over 2m d cubed p? Trying to remember. I think for each moment, it's the square root of 2m pi over beta to the third power, and the 3 comes from the 3 dimensions of space. Okay, so it's 2m pi over beta to the 3/2 power. Okay, so we have that. But now we have another factor coming from here. The other factor coming from here looks exactly like, oh, what about, first of all, the theta integration? What does the theta integration give? 2 pi. It's sort of like the volume, except the volume is just 2 pi. The volume of the theta variable is just 2 pi. So if I really want to keep track of all the numerical constants, there's a factor of 2 pi, and then I get to erase the d theta. All right? And then there is the integral dl. Now, the integral of dl is the same kind of integral that we did here. Again, it's a Gaussian integral, easy to do. Instead of being to the third power, since there's only one angle, not 3 angles, there's only one angle, there's just a single integration to do here, but it's the same kind of integration. The only difference is, instead of where you see m, you now have I. So the next factor would be square root of 2I pi divided by beta, and that's it. One more factor. Another way of saying it is there were 3 directions of space plus an extra internal direction, and so the third power of 1 over beta got replaced by the 4th power of 1 over beta. 1 extra power of 1 over beta. The extra volume coming from the integration over the position of the circle, that's just a numerical factor of 2 pi. This is the partition function for a single diatomic molecule of a particularly simple kind. Okay? Now notice I have restricted the molecule to move in a plane. A real molecule can move around in all 3 dimensions, and it gets a little more complicated, but I wanted to do the simplest example. In the notes is the example where the rigid molecule can move around in 3 dimensions. All right, so this would be the simplest diatomic molecule. And and we would raise that to the nth power and divide by n factorial for a gas of n particles. Okay. And as I said, the only new thing is this. Let's put a box around it. The simple diatomic, the simplest possible diatomic molecule. Oh, exactly the equations I needed. I think we've seen these before at some point in the history of our studies. Yeah, it's a Newtonian limit. Yeah, it's a geodesic equation in the Newtonian limit. That's what's going on here. All right. Okay, so let's rewrite it. No, let's not rewrite it. Let's take its logarithm. The main thing that we're interested in usually is the logarithm of the partition function. Logarithm of the partition function is, as always, proportional to n. Well, let's be a little bit. Let's actually just do it. N minus n log n factorial, coming from the n factorial in the denominator, volume to the nth. Sorry, plus n log volume plus n log of the volume. You can combine these together so that it involves the logarithm of the density. I showed you how to do that using Stirling's approximation, but I'm not going to bother even doing it. We've done that before. You would do exactly the same thing here. And then you get plus or minus 3/2 logarithm of beta. There's also the logarithm, 3/2, the logarithm of 2m pi. I'll include that at the end over here. But let's not worry about it for the moment. And now there is, oh, sorry, you didn't correct me. It's 3n log beta, 3/2n log beta. But now, from the beta dependence in the last term there, let's write it explicitly, minus another n log beta. And then a whole bunch of constants. Logarithm of 2m pi, logarithm of 2I pi, all those constants, logarithm of 2 pi, all the various constants. Let's just add them up here and call it constant. A numerical addition to the log of the partition function, which will not contribute to anything interesting.
You got a factor 2.
I don't think the first term should be just log n factorial.
Yeah. Good, thank you.
Or minus log n.
Yeah, minus log n factorial.
That's correct.
And then you get a factor 2 in the second to the last term. Get it divided by
Which one?
n log beta.
Here?
Next one.
N log beta over, yeah, n over 2 log beta. Okay, so it's simple. It's just one extra coordinate added to the 3 coordinates, but I wanted to keep them separate because just to show that they come from different places. All right, now what is the energy per molecule? The energy per molecule is just a derivative of log z with respect to beta, with a minus sign. All right, that will give us minus, or when the minus sign is accounted for, it will give us 3n over 2 times 1 over beta. Differentiate log beta, you get 1 over beta, but that's just the temperature, so let's just call it temperature. 3n over 2, and that's the classic formula for the point particle gas. But now there's another term, plus 1/2 n times the temperature. So the whole upshot is that the energy per particle is 2nt rather than 3/2 nt. In other words, there's just more energy there for a given temperature. There's more energy there because the rotational degrees of freedom get excited. Okay, so that's what this is here. Now there's a puzzle, and the puzzle goes as follows. Imagine that you now took the limit in which the radius of the molecule got smaller and smaller and smaller. shouldn't you eventually get closer and closer to the point particle limit? After all, is it really reasonable that you can tell, imagine that this rod which connects one point particle, we're thinking about a model now of 2 point particles connected by a rod, and now imagine shrinking the rod until the 2 point particles are 10 to the minus 10 Planck distances apart. In other words, until the distance between the points is infinitesimally smaller than any distance scale that we ever think about in physics. Shouldn't it become the point particle? If it does, it means that you should only have 3/2 nt energy in the system. But somehow this doesn't go away. It doesn't depend on the radius. Incidentally, where in this formula up there is the radius of the molecule embedded? It's an I, and that adds to this constant here. But the constant doesn't get differentiated to calculate the average energy. So no matter how small you make this molecule, no matter how tight you make that molecular bond, this term does not go away. Well, this gets a little bit crazy now. Do we have to worry separately about the electrons rotating? Even an atom is not a point particle. An atom might contain 20 electrons going around it. Do we have to include 20 additional contributions like this coming from the 20 electrons going around it? And perhaps the electrons themselves secretly have some, the nucleus, of course, has many constituents and so forth. So even a simple atom is not a point particle. It contains many, many degrees of freedom. If you were to do the classical calculation, you would find out that there is a 1/2 nt for each internal degree of freedom of the atom. This doesn't make a lot of sense. There should be no way that you could tell from the properties of a gas at a low temperature. Certainly at a very, very high temperature, where the molecules may collide so hard that they would knock each other into smithereens and so forth, you could tell that the molecules were not point particles. But at very, very low temperatures, where the velocities are very small, momenta are small, how can it possibly be, and the gas is very dilute, particles are far from each other, how can it possibly be that the thermodynamics, the energy of the system in particular, remembers that the atoms are composite? Shouldn't be the case. The solution to this puzzle, and we'll do it now, the solution to this puzzle is quantum mechanics. So I thought I would just work out the quantum mechanical formula and show you how that comes about. Not show you how it comes about, we're going to pretty much assume a formula, and show you what actually does happen for a real molecule, how the paradox gets resolved. All we have to know, the only thing we have to know about quantum mechanics is that angular momentum is quantized. That angular momentum is not a continuous variable. It's a variable which comes in discrete multiples of a basic unit, and that basic unit is Planck's constant. All right? So let's go back. Let's go back to this formula over here. I think we don't need this anymore. Let's go back to the energy, to the rotational energy, E equals L squared over 2I. And now write that the possible values of the angular momenta are not a continuous variable, but that L is quantized in units of, let's call it N times h bar. Planck's constant times h bar. Okay. L is equal to N times h bar. H bar, of course, being a very small number, so that means the steps between different values of the angular momentum are very small, but nevertheless it's not continuous. And then we can write the energy not as L squared over 2I, which is correct, but as N squared H bar squared over 2I. Do I have that right? I think I have that right. And what is the variable now which distinguishes one state from another? N. And incidentally, N can be any integer, positive or negative. Why positive or negative? Well, negative angular momentum corresponds to rotating in one direction, positive angular momentum in the other direction. Angular momentum 0 just means not rotating at all. This is the energy of the molecule quantum mechanically. And that's all that we need from quantum mechanics, that we replace the sum over states by the sum over n. And that's it. So let's write down now what the partition function is for the quantized angular momentum. Incidentally, there is no real change associated with the first term, the p squared over 2m. Quantum mechanics, we should do quantum mechanics to really do it correctly, but it gives the same answer. It's the L squared over 2I, which is most sensitive because of the quantization of angular momentum. Momentum itself, linear momentum, is not quantized as a rule, at least in a very big system. It's the angular momentum which is quantized. Okay, so now let's write down the partition function, again, for a single molecule. And Z now becomes equal to the sum over n of e to the minus beta times the energy, which is n squared h bar squared over twice the moment of inertia. That's it. Good. The sum over n here is too hard to do. There's no simple closed form for summing over n, right? So we can't do it. But we can do enough. We can do some approximations which will which will show us exactly what's going on. Sometimes approximations are more illuminating than an exact formula. First of all, there are two regimes of temperature which behave quite differently, or which are extreme situations. Very high temperatures, very low temperatures. Let's examine the two cases of very high temperatures and very low temperatures. Very high temperatures means beta very small. So keep that in mind. High temperatures, T is 1 over beta. I always get myself confused, and I always naturally first think when temperatures are high, that means large beta. But then I have to correct myself and say, no, when temperatures are high, beta is small. When temperatures are low, beta is high. So keep that in mind. Okay, what happens, which should we do first? Let's do first high temperatures. High temperatures means beta is small. And let's take this quantity here and imagine plotting it. Let's see, I'll plot it over here. Horizontal axis is n. N is an integer. And what I'm plotting is the thing in this exponential here. Right? It has a value at each integer. Now, when beta is very small, forget for the moment the quantization. Let's just look at this as a function of n. When beta is very small, temperature is very high, this is a very slowly varying exponential. When beta is very small, it's a very slowly varying exponential. And to a high approximation under this circumstance, the sum over the values of n, each delta n here, delta n equals 1. So each one of these is separated by 1 unit of n. The height is the function, and so the contribution of each one of these strips here is basically just the area of it, and so forth. To a high approximation, as long as this is smooth and gentle enough, which means the temperature high enough, this sum can be replaced by the integral over n. All right? The integral over n, we're replaced by the integral over n, and if we do replace it by the integral, we're back to the classical calculation. Instead of integrating over angular momentum, we're integrating over n, but that doesn't make any difference. N is proportional to the angular momentum. It's the same integral except for a numerical constant, and we don't care about numerical constants very much. So the first thing is that at very high temperatures, it simply reproduces the same answer as the classical calculation, at least for everything interesting. The sum can be replaced by the integral because the function is extremely smooth and slowly varying. Okay. On the other hand, all right, so that's one fact. High temperatures classical answer. And what was the classical answer? Not 3/2 kT, not 3/2 T for the energy per molecule, but twice T. Or, not 2 over T, twice T. In other words, the rotational energy is excited just as it would be in the classical case. On the other hand, let's go to low temperatures. At low temperatures, beta is very big. That means this function is a very rapidly falling function. And in fact, if beta is big enough, if the temperature is small enough, the function varies enormously before it even gets to n equals 1. And then between n equals 1 and n equals 2, it falls even further, and so forth. To approximate such a rapidly varying and rapidly falling function by the integral is nonsense. That's not a good thing to do. It's not approximately given by the integral. In fact, the smart way to do the calculation is just to recognize that each succeeding term is very much smaller than the previous one, and just approximate it by the sum of a small number of terms. In particular, just approximate it by the first two terms in the sum here. Why the first two terms? Well, let's just take the first term to begin with. What's the first term? The first term corresponds to n equals 0. Remember, we have to sum over all positive, negative, and 0 values of n. Right? Positive and negative give the same answer because it's n squared here, so we can just, for practical purposes, sum over only positive n and 0. The first term is just 1. That is not a very interesting partition function. The first term is just 1. Anything you differentiate it with respect to gives 0, and it simply says that the energy, the rotational energy now, the rotational energy is 0, okay, for very low temperatures. Let's find the first, and that's good because, well, we'll see what it does in a minute. We'll see what it does in a minute. Okay. So in order to get any kind of interesting answer and to see how the energy, rotational energy, does depend on the temperature, we at least have to go to the next term. So the next term is n equals 1 plus e to the minus beta h bar squared over 2I. Now, when beta is very big, not only when beta is big, there are various situations.
Does that occur twice?
Yeah, it does occur twice. Thank you. That's good. It occurs twice, once for positive and once for negative. Very good. Okay. Notice that there are two distinct ways that might make this thing small. One way is that the temperature is very large. Sorry, opposite. The temperature very, very small. If the temperature is small, beta is large, and then this correction here is very, very insignificant. But there's another way. Even if the temperature is not so small, if I is very small, okay? If I is extremely small, it means the coefficient 1 over I is very big. So that's tantamount to just saying beta is larger. So there are two ways to make this term insignificant. One of them is low temperature, but let's fix the temperature. Let's take the temperature to be fixed and do something different. Just shrink the molecule. What happens when you shrink the molecule? When you shrink the molecule, this I gets smaller and smaller. Beta over 2I gets bigger and bigger. And even if the temperature is not so low, you get driven into the situation where this function just drops to 0 like a bomb. And the integral is silly. You don't do the integral. The good approximation is just to add a small number of terms, each one getting much, much smaller than the previous. What's the next term? Every term has a 2 because the angular momentum could be positive or negative. What's the next term? E to the minus 4 h bar squared over 2I. Now, e to the minus 4 beta. Now, this is the fourth power of this. If this is small, the fourth power of it is really, really small. Okay? The next one after that would be the ninth power of the same thing, and so forth and so on. So in a situation where either beta is large or I is small, then we can safely ignore the higher terms. We might think we could also safely ignore this, but since we're trying to find out what the beta dependence is, it's better to keep it because the first term doesn't have any beta dependence at all. All right, so this is a good approximation for very low temperatures. What's the logarithm of this? Remember, this is a very small quantity. The logarithm of 1 plus a small quantity is just a small quantity. Oh, incidentally, of course, if there are n particles, we just raise this to the nth power. Now, so far, this is just the rotational energy, and I'm only concerned with the rotational energy now. The other parts of it are still there. The logarithm of z is just going to be twice e to the minus beta h bar squared over twice I times n. No, it's, yeah, twice 2n. Okay, so now we can compute, once we know the logarithm of z, we can compute the energy stored in rotation. Okay? We can compute the energy stored in rotation. All we have to do is differentiate log z with respect to beta. So the derivative of log z with respect to beta is, of course, 2n. And then differentiating with respect to beta will give us a minus sign. It will give us the same e to the minus beta h bar squared over 2I. And then we have to differentiate what's in here with respect to beta. That will give us h bar squared over 2I. I think I have that right. Let's see. Differentiate, yeah, well, it looks right. Okay. That's the derivative of log z with respect to beta. The negative of it is the energy stored in rotation. And the energy per particle would just be divided by n. This does not look like the classical formula. The classical formula was just plain 1 over beta. Okay? It was just 1 over beta, which meant temperature. The energy stored in rotation was just temperature. This formula has the feature that when beta is very big, when temperature is low, or when I is very small, the contribution is exponentially small. Exponentially small. This is not so significant here. This is the significant factor. and the energy stored in rotation is minute, even if we keep the temperature fixed, if we let I shrink to 0, if we shrink to the point particle limit, this simply disappears. That's the solution to the paradox of molecular structure, and why it is that the molecular structure degrees of freedom do not get appreciably excited, at least at low temperatures. At high temperatures, they do get excited. So an interesting question is, where is the crossover point between the classical formula and this? Now remember, this was an approximation. You cannot take this approximation and study it for high temperature. Why not? Because the high temperature behavior involves this whole sum. For high temperatures, beta is not small. These are not small results, and you've got to add them all up. For low temperature, that's the place where you can just truncate the sum and say only appreciable contribution comes from the first term here. So you can't mix the approximations. One approximation, high temperatures, is to substitute for sums integrals, and that gives you the classical formula. The other approximation for low temperatures is just to take one or two the contributions. Where does this formula go from one thing to another? And I'll tell you where it happens. Where is the crossover from one type of behavior to another? It's when the temperature is such that the classical energy, which would be 1/2 T, 1/2 T would be the classical answer, when that is equal, or approximately equal, to the energy of the lowest rotational excitation. Okay, what's the energy of the lowest rotational excitation? Here's the energy. N equals 1, h bar squared over 2I. For temperatures lower than this, there just is not enough energy to excite the atom into the molecule into rotation. There's just not enough energy. The temperature is not high enough to overcome the separation between energy levels. Okay? At high temperature, there's no problem. You can excite the rotational degrees of freedom very easily. And it's when the temperature gets to be such that it corresponds to 1 quantum's worth of rotation, that's about where the transition from one thing to another happens. So as long as the temperature is lower than this, then rotational degrees of freedom don't get excited. That depends on the moment of inertia. Okay? If we wrote the moment of inertia in terms of the mass and the radius of the molecule, we would find out that when the radius of the molecule goes to 0, in other words, when the moment of inertia gets extremely small, the temperature needed to excite that rotational degree of freedom gets infinitely big. All right, so that's the resolution. Quantum mechanics sort of truncates and the contribution of very small angular momentum, and you need a certain amount of temperature before you start to get the molecule rotating.
And
Yeah.
there's a Boltzmann constant in here.
There is a Boltzmann constant. My convention is such that what in textbooks is called K, and I'll use little t to represent the textbook definition of temperature, then big T is K times little t. So yes, there is a Boltzmann constant in here, and which you would need to put in if you were actually doing some numerical work. So if you wanted to find out at what temperature measured in units Celsius or units Kelvin, you would want to put Boltzmann's constant in here. That would make the temperature even bigger. So yeah, okay. So let's see. K. Okay, so it's kind of interesting to put in some numbers into here and to find out at what temperatures do you start to excite the rotational molecular degrees of freedom for a molecule with reasonable parameters.
Can I ask you a question?
No.
In that regard, is that temperature generally below the, let's say, the point at which a normal gas or air or oxygen would turn to a liquid? Or is this a very low temperature, or is it a room temperature?
No, it's a fairly high temperature. No, it's higher than room temperature.
So the oxygen atoms in this room, it's hard to imagine that they're not rotating, that they're not spinning at just from.
For oxygen, no, for oxygen is probably big enough that's, yeah, no, for oxygen, I was actually thinking about, I was thinking about hydrogen and its electronic structure. For hydrogen and electronic structure, it's a rather high energy. For oxygen, I suspect it's near room temperature. I'm not even sure. I'm not sure. But at low enough temperature, there is a low enough temperature where these are frozen out, where these degrees of freedom are frozen out. Or another way of saying it is that there's a moment of inertia for fixed temperature, which if it's too small, will freeze out these degrees of freedom. Yeah.
Very non-classical.
Yeah. I think the temperature for molecular things is fairly low, probably lower than room temperature for nice large-sized molecules.
Like a hydrocarbon chain or something.
Oh yeah, no, they're and for hydrocarbon chain, yeah, I mean you have zillions of degrees of freedom, so it's nowhere near 3/2 or 2 kT. It could be a zillion kT, depending on the number of ways that the molecule can flap around. Right, okay, so that's the basic physics of the diatomic molecule and why at low temperatures or very, very small molecules, you don't have to worry about the structure. Yeah,
One intuition is that this would affect the specific.
louder.
An intuition is that this would affect the specific heat you get.
Yeah, absolutely.
Specific heats at-
Absolutely. Yeah, certainly. Right. It certainly does affect the specific heat. For example, just at low temperatures or small molecule size, but at low temperatures, the specific heat will resemble the specific heat of the point molecule system. And at higher temperatures, the specific heat, or the heat capacity, will be bigger. Is that what you were asking? Good.
Question. If you, at very low temperatures, if you add a little bit of heat,
Yeah.
not enough to, flip the rotational energy over, then that energy must be manifested in the other.
In the translational degrees of freedom. No, that's correct. No. In other words, I wouldn't, yeah, what you say is absolutely right, but I would say if you raise the temperature a little bit, instead of saying add a little bit of heat, you can imagine adding a little bit of heat without changing the temperature. One way to do it would be to add a little bit of heat but expand the gas. So I think the right language is to say if you raise the temperature a little bit. Technically speaking, I wouldn't want to say if you add a little bit of heat, because you can add a little bit of heat in many ways, including adding heat and expanding the gas or expanding the volume, and then you wouldn't change the temperature. So it's the temperature which counts here. All right. Good. All right, are we happy about diatomic molecules? All right, I was going to talk about magnets a little bit, but I think I will turn to something else and come back to magnets next time. Black hole thermodynamics. And this is the kindergarten version of black hole thermodynamics. By kindergarten version, I mean it's based on, and you're not allowed to push me too hard for precision, because the precision really comes from studying quantum field theory in the vicinity of a black hole. But the idea is all right, and what I'm describing to you now is very much Bekenstein's first explanation of why black holes have entropy, and then given that they have entropy, the various consequences of that. And they're applications of things that we've talked about. But as I said, the logic is not going to be as tight as you might like. But nevertheless, it does explain what's going on pretty well. All right, let me just remind you about the important things about black holes. You don't have to know very much about what a black hole is. What you need to know is that it's an object which has a mass and a radius. Now the radius is now the radius of the horizon, a radius, and it's the Schwarzschild radius, which I won't bother denoting r sub s, because it's the only capital R that will be in the problem. And the connection between these two, incidentally, a normal gas and so forth has both an energy and a volume, or if it's a spherical container of gas, it has an energy and it has a radius, and they're independent variables. You can vary both of them simultaneous at will, and it's a two-parameter system. One is a control variable, the volume. The other is, you can also think of it as a control, but the other is the energy. The black hole has only one parameter, or at least the simplest kind of black hole, the Schwarzschild black hole, has only one parameter, either the mass or the radius, because the mass and the radius are connected with each other, and they're not independent variables. Okay. What's the connection between them? The connection between them is that the radius of the black hole is equal to twice the mass times Newton's constant divided, I think, by c squared. I'm going to keep, for the time being, I'm going to keep the c's in the formula. And because there is this connection, you think of it as a one-parameter system which is completely controlled by the energy of it, and you don't have to think about a separate control parameter which is the size of the system. Okay, this I think is the only real thing that we need to know about black holes. We also need to know that black holes swallow everything that come in their vicinity. And here's what I want to do. I want to add to the black hole one bit of entropy, one bit of information, the minimal amount of information that I can add to the black hole. In fact, what we're going to imagine is we're going to start with a very small black hole, and we're going to imagine building up that black hole to a larger size by throwing in bits of information, one bit at a time. Now, what does a bit of information mean? A bit of information for us is going to mean throwing in a particle. Either there's an extra particle in the black hole, or there isn't an extra particle in the black hole. Okay? So we're going to imagine throwing in particle by particle and filling up the black hole until it gets to a bigger size by adding to its mass. It's very much like filling up a bathtub full of hot water by adding molecule by molecule. And here's the kind of question we might ask. If we add a certain number of molecules, how high is the level of the water? Well, that's an easy problem. You know, if you know the volume of a molecule and you add n molecules, you increase the volume of water by n units and so forth and so on. We know how to do that problem. Here now, we want to ask, how does the radius of the black hole grow as you add bits of information? Okay, so we're going to drop into this black hole particles. The simplest kind of particle to throw into the black hole is a photon. All right. Why? Because it's the easiest kind of particle for our purposes. So let's imagine photon by photon, we drop photons into the black hole, but we have to be careful not to add more than one bit of information when we throw a photon into the black hole. Now, supposing, first of all, we had a big black hole, and we threw in a photon, and that photon was a well-collimated photon from a laser beam with a short wavelength, and the size of the black hole was a kilometer. Well, throwing in that one single photon is a lot more than one bit of information. And the reason is there's all kinds of information stored in the location that you threw in the photon. In fact, how many bits of information does it take in order to describe exactly where you threw in the photon? Not exactly, but with a certain accuracy. So I give you a certain accuracy and I say, how many bits of information are there that are coded, or that it takes to code the location of where the photon goes in? And the answer is, well, you have a couple of coordinates, an azimuthal and a polar angle to describe. You're going to describe those coordinates to a certain degree of accuracy, which means that a certain number of binary digits are necessary in order to specify where you threw in the photon. The number of binary digits is roughly the number of bits of information that are stored in the question, or the answer to the question, of where that photon fell through the horizon. So generally, throwing in a photon like that is much, much more than one bit of information. But if I throw in a long wavelength photon, a photon whose position uncertainty is so large, larger than the whole size of the black hole, then there's no sense. If we take a long wavelength photon whose position is quantum mechanically as uncertain as the whole size of the black hole, then the only question we can ask is, did the photon get in there or didn't it get in there? Is there an extra photon in the black hole or isn't there? So
So is that true even though when the photon enters the black hole, it gets smeared across the horizon?
the photon, of course, is quantum mechanically smeared across. Yes, that's true. Even if the photon gets smeared across.
If it's smeared across the horizon, how is that positional information retained? It would seem that when it smears across the horizon, you lose it.
The point is, yeah. Let's come back to the bathtub full of hot water. Okay? We drop in a molecule at a certain definite place inside, on the surface of the hot water. Very, very quickly, for all practical purposes, in particular the purposes of taking a bath, we do not care where we dropped in that molecule. But information is conserved. To the person, to Laplace's master of the universe who can follow every single particle and so forth, that information is not lost. So when you throw in a single molecule into the bathtub full of hot water, the entropy goes up by more than 1 unit. The more, the better you know where that molecule went in. The fact that it later gets distributed throughout the entire bathtub, or that it gets delocalized, the information gets delocalized over the whole bathtub, that's secondary. The amount of information you threw in was whatever it took to specify where you threw in that molecule. So it's this conservation of information business, conservation of microscopic information. Same thing in a black hole. The details, the undecipherable details that are too microscopic to see on the surface of the black hole, remember the things which constitute the entropy, remember where the photon was thrown in. All right, so our best strategy then is to delocalize the photon as much as possible, and then there won't be any memory of where the photon went in, because there was no sense in which the photon had a definite location. You say, well, why not just take an enormously long wavelength photon? And the answer is that wavelengths, photons which have a wavelength, now this is something I'm going to just ask you to accept, that the question of whether the black hole is an absorber or a reflector is dependent on the wavelength of the radiation that you throw in. If the radiation has short wavelength by comparison with the Schwarzschild radius, the black hole is a complete absorber. It will absorb radiation of shorter wavelength than the size of the black hole. On the other hand, for waves which are longer wavelength than the size of the black hole, they just get reflected. The black hole is almost a perfect reflector of waves which are longer wavelength than the size of the black hole. That you have to accept.
So would it refract it or reflect it or just bend it? Could that be?
Well, not bend it, but yeah. It'll bend, yeah. Right, it'll bend it. Yeah, it'll bend it. Just like a spherical mirror. It'll do whatever a spherical mirror does. I don't know, what does a spherical mirror do? Reflects and bends and does a variety of things. It'll behave very much like a mirror. So,
Is it longer than the radius or longer than the diameter?
somewhere in that neighborhood. We're not going to keep track of factors of 2. So, the reflectivity is a continuous function, and it goes from no reflectivity at short wavelengths to almost perfect reflectivity, and in fact, perfect reflectivity at very long wavelengths. And the transition region is in the region of the Schwarzschild radius. And there's a specific formula that you can work out, which I don't remember. It's not important. Okay. So the strategy of throwing in the very, 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 very long wavelength photon will backfire. The photon just won't get in for sure. Right. On the other hand, it's good enough to throw in a photon whose wavelength is about equal to the radius of curvature, the radius of the black hole. It has some chance of getting in, 50% chance of getting in, 50% chance of not getting in, I don't know. But since it's delocalized on the scale of the whole horizon, there's no sense to ask where it fell in. And so all there is then is the question, did it get in or didn't it get in? One bit of information. So throwing in a photon of wavelength lambda equal to the Schwarzschild radius, I said I wouldn't write R sub s, but I wrote it anyway. That's the best strategy for throwing in one bit of information. Now, next question. How much does the energy of the black hole increase when you add one bit of information? Well, the answer is it increases by the energy of a photon whose wavelength is this big. Okay, so you have to remember then what the energy of a photon is in terms of its wavelength. I will remind you. The energy of a photon, let's write it E sub gamma, gamma for photon. The energy of a photon is h bar over lambda times the speed of light. That's an elementary quantum mechanics formula. Einstein, is that Einstein's formula? Yeah. It's the same as E equals h nu. Okay? E equals h bar c over lambda. Is it h bar or h? I think I would take back just h. Just h. But we're not going to be keeping track of factors of 2 anyway. So my h's may, or 2 pi for that matter. The difference between h and h bar is a factor of 2 pi. I'm not really keeping track of that. And since I'm so used to writing h bar, no, you can't do that. Illegal. But you can set equal to wiggle. Equal to wiggle. All right. Strictly speaking, this means approximately equal to. Proportional to is better, but close enough for our purposes. That's how much the energy increases. So when you throw in one bit of information, the energy of the black hole increases by this amount. Okay? Next question. How much does the radius of the black hole increase? Now, we have a formula that tells us the radius in terms of the mass. Mass, of course, is energy. Mass is energy. So when apart from a factor of c squared, mass and energy are the same thing. So when I say that the energy of the black hole increases by this much, I'm also saying that the mass increases by a related amount. All I'm using is E equals mc squared. So what is the change in the mass of the black hole? You just divide the change in energy by c squared. So the change in mass, when you throw in one bit, is equal to the change in energy, h bar c over lambda. Oh, but now we can replace, first of all, we can replace lambda by R Schwarzschild. Might as well do that. H bar c over R. That's the change, that's the additional energy that you throw in, and now I think we have to divide that by c squared because of the c squared here, and so the mass of the black hole changes by this much. How does the radius of the black, and that's a nice formula. Throw in one bit of information, that's how much the mass increases. Okay. How much does the radius of the black hole increase? Well, we have a formula relating radius to mass, so in principle we also have a formula relating the change of radius to the change of mass. All we have to do, let's solve this equation for the mass, let's get rid of some of the mess over here. Let's see. M is equal to c squared r divided by 2g. Do I have that right? Okay. And 2's, let's forget 2's. 2's are not important to this calculation. All right. Proportional to. We're trying to make an estimate. This is an issue of making an estimate. All right. M is c squared r over g. Why did I do that? I don't even know why I did that. Well, it's smarter just to take this formula as it is and to multiply. Here's the change in mass. Let's multiply it by twice g over c squared, and that'll give us the change in r. What I want is the change in r. So let's just multiply by g over c squared. The change in r is g over c squared, let's forget the 2, g over c squared times the change in mass, which is h bar over r times c. So I've now figured out how much the radius of the horizon changes when I throw in one bit of information. Here it is, g, h bar, small because h bar is small. It's also small because c is large. Here is the radius itself. So the change in radius is inverse to the radius itself. The bigger the radius, the smaller the change in the radius when you throw in one bit. But let's multiply the equation by r. That says that r times the change in r is equal to g h bar over c cubed. One bit of information, r times delta r is equal to g h bar over c cubed. Now what is r times delta r? It's just the change in r squared to within a factor of 2. And what is r squared? It's the area of the horizon. So here's what we found out. That the change in the area of the horizon, when you throw in one bit, is a universal constant It does not depend on the size or the mass of the black hole. The change in area is always g h bar over c cubed. A universal constant unit of area, this has dimensions of area, where every time you throw in a single bit, you increase the area by the same exact amount. All right, so now if we imagined building up the black hole from a small black hole by throwing in bits of information, at the end of the process, we would discover if this is the change in the area when one bit of information is thrown in, how much does the area change when you've thrown in S for entropy, when you've thrown in S bits of entropy? Just multiply it by S. One bit changes this much. S bits, the change, and by now, if we build up the black hole from a small black hole, we can just write that the total area is equal to g h bar over c cubed times the entropy of the black hole. Or we can invert the relationship and say, hey, we made a discovery. Black holes have entropy equal to c cubed over h bar g times the area. Now that's not an equality, that's an estimated value. Where was the estimate? Well, many, many places where we made estimates. This is the Bekenstein formula. And what it says is that that's how much hidden information is there in the black hole. It's kind of interesting. This is one of the few places in physics where h bar occurs in the denominator. Usually, quantum effects are small. The existence of an entropy is a kind of quantum effect, but just think about it for a minute. What it says is that in the limit of classical physics, the entropy doesn't go away, the entropy becomes infinite. Quantum mechanics is not what gives the black hole entropy. Quantum mechanics is what prevents the black hole entropy from being infinite. Why would black holes have so much entropy? And the answer is very simple. You can hide an enormous amount of information in a black hole. Take the Encyclopedia Britannica and throw it into the black hole. You can't tell the difference between that and throwing in a few chickens, right? You can't tell the difference at the end. So there's a lot of information potentially storable in a black hole, or a lot of hidden information that's storable in the black hole. And in classical physics, it's not that there's no hidden information hidden in a black hole. It's that the potential amount of information is infinite in a black hole. It's quantum mechanics which keeps it from being infinite and gives you a finite entropy. All right, so that's the origin of entropy in black hole physics. Let's talk about temperature. We could do this in two ways. I like one way better than the other. Here we have the entropy written in terms of the area. The area can be written in terms of the radius, and the radius can be written in terms of the mass, and the mass can be written in terms of the energy. So in principle, we have a connection between entropy and energy. When we know the connection between entropy and energy, we can compute temperature. dE equals T ds. But we can short circuit this. We can also say that the definition of temperature, when you write dE equals T ds, basically this says that the definition of the temperature is the change in energy when you change S by 1 unit. If ds is just 1 unit of entropy, we can write, approximate delta E equals T delta S. And if we change the entropy by 1 unit, then the temperature is just the change in the entropy. The change in the energy. Well, let's go back. That's what we started with. Here is the expression for the change in energy when we throw in 1 bit of information. So this then is the delta E on the left-hand side, and on the right-hand side, delta S is equal to 1 unit of entropy, and so this must be the temperature of the black hole. H bar C divided by its radius. We can also write this, and there's a numerical constant. There's a numerical constant, but we can also write this as H bar C divided by the Schwarzschild radius, which is 2mg. All right, the honest answer happens to be, I think, 8 pi here. But that's not important to us. Let's not fool around with that. Let's just leave it as mg. That's the temperature, the change in entropy when you add 1 bit. So this is an application of that idea. And it's very interesting and unusual. It's unusual because remember, m is the energy of the black hole, and the temperature decreases with energy. So this is a very unusual situation where a system's energy, where a system's temperature is inverse to its energy. How many systems have you ever heard of whose temperature increases when the mass decreases? Or when the energy, whose temperature increases when the energy decreases? Anybody know a system that does that other than a black hole? Okay, I'll tell you. They're actually extremely common. Hmm? No. They're not that common. A star. A star. What happens to a star when it runs out of fuel? And it radiates away its energy. As it radiates away its energy, it shrinks, and what happens to its energy? What happens to its temperature? Temperature goes up. As the star runs out of fuel, it heats up. Its temperature goes up. What happens is, let me give you an example first of all. Just a planet orbiting the sun. Suppose there's a little bit of friction. A little bit of friction, or it radiates away energy in the form of gravitational waves, anything which decreases the energy of the planet as it goes around. It starts to orbit inward, and it loses its energy by increasing its negative gravitational energy. Its energy increases because its gravitational energy goes up, but its gravitational energy is negative. So it spirals in, losing its energy, but what happens to the velocity as it spirals in? The answer is it goes up. It loses more potential energy than it gains kinetic energy by a factor of 2. So as it spirals in, it loses energy, but it speeds up. And because it speeds up, if these were individual molecules falling into the gravitating object, it would mean that its temperature goes up. So this is an odd situation, all right, but it's not all that uncommon that the temperature increases as the energy decreases. The smaller the black hole, the higher the temperature. The smaller the energy, the higher the temperature. Okay? The bigger the black hole, the lower the temperature. So a black hole of stellar mass, a black hole of mass of 1 solar mass, has a temperature of something like about 10 to the minus 8th degrees Kelvin. The temperature is inversely proportional to the mass. So a black hole at the center of the galaxy with a mass 1 million times bigger or 1 billion times bigger would have a temperature 1 billion times smaller. Of course, there are other reasons why black holes have temperature, having nothing whatever to do with quantum mechanics and Hawking and Bekenstein and all of that. They may have temperature, observational temperature, for a totally different reason. Namely, there may be gas swirling around them, and as the gas swirls around them, it heats. And as it heats, it gives off light, but eventually that gas will be absorbed by the black hole, and when the black hole is in an environment which is otherwise empty space, it has a temperature, and the temperature is inverse to its mass. So that's the application of some of the thermodynamic relationships and some of the ideas of information, energy, entropy, temperature, and how they fit together to, in a surprising way in a black hole. Yeah.
By temperature here, do you mean temperature inside the black hole or at the horizon?
No, I mean the temperature seen by an observer far outside the black hole.
Is that at the horizon?
It's the temperature seen by somebody far away from the black hole, detecting photons which are coming out of the black hole and measuring their energy and asking what does that correspond to in the way of a temperature. We haven't done anything about black body radiation yet. You stand far away from the black hole. It's exactly the same as the sun. Is the temperature that we ascribe to the sun the same as the temperature that we would measure if we lowered a thermometer down to near the sun? The answer is no. The temperature that we ascribe to the sun is a little bit less than the temperature that you would ascribe to the sun if you lowered a thermometer down. And the reason is the temperature that a thermometer sees is dependent on the energy of the photons which are hitting it. The energy of a photon, when it climbs up out of the gravitational field of the sun, the energy of the photon decreases. So the energy of the photons that we measure far away from the sun is a little bit less than the energy that we might have ascribed to it if we stood right at the surface of the sun. When we do the thermodynamics of the sun, we do it as observers who are far away from the sun. That's the appropriate way to do it. And the same thing with a black hole. We do it from the point of view of somebody far from the black hole. If we got close to the black hole and measured the temperature, it would appear higher, just for the same reason that the temperature at the surface of the sun is a little bit higher. How do we detect the fact that the temperature at the surface of the sun is a little bit higher than the temperature that we actually measure? How would we detect it? From the position of spectral lines. The spectral lines that we see far away look a little bit less energetic than the spectral lines that we would expect from chemical emissions near the surface of the sun. So this is the correct temperature to ascribe to somebody observing the sun from far away. No.
So, but would
It's not the sun, it's the black hole.
would it be correct to say that the maximum amount of energy per volume is what's inside a black hole?
The maximum amount of, say it again.
The entropy per unit volume, or maybe its area, would be basically what's inside a black hole. That's the most.
I think this is what this is telling you. The fact that the entropy is proportional to the area is that, at least when viewed from outside, the black hole doesn't have an interior. All it has is a surface. And this is closely connected with the fact that somebody on the outside dropping things into a black hole never really sees them cross the horizon. They accumulate in layers near the horizon as seen from outside. So observations from outside the black hole will always say that the amount of stuff that you can store on the black hole is stored on the surface of the black hole. And it's closely connected with this fact. Yeah. Yeah.
If you take this temperature and plug it into the black body radiation formula, do you get the right amount of radiation?
Luminosity. Let's do it. Yes, you do. The coefficient numbers are slightly off, but yeah. Well,
As long as we have the C there.
as long as you have what?
As long as we have HC over NG, there is a C squared that we drop from R.
Well, maybe so.
So there's really an HC.
Yeah, you're right. It sounds right.
Is entropy proportional to the number of bits or the log of the number of bits?
No. Entropy is the number of bits. The number of states is the exponential of the number of bits. So entropy is itself a log. Remember, it's the average value of the logarithm of some probability distribution. Entropy is a log. Sorry, the number of bits is itself a log. For example, if you have n bits, those are n possible two-state systems. How many states are there? 2 to the n. What's the entropy? It's the log of 2 to the n. N. Log of 2 to the n is n. So you don't want to take another log on top of that.
Did you say the area for 1 bit is equal to the, earlier class, equal to the Planck's length?
I didn't say it, but that's right. The area, yeah, here, okay, so here it is, c cubed h bar over g. And now we could stick in some numbers. Well, the right way to say it is 1 bit of information, one bit of information corresponds to an area. Let's call it the area of a bit. The area of a bit is h bar g over c cubed. H bar is tiny, g is tiny, c is huge. This is a very small number, 10 to the minus 66 square centimeters. And it's the Planck area. Yeah, I should have, right. It's the definition of the Planck area. The Planck length being just the square root of this. But it's very, very clear that the fundamental quantity is an area, not a length. Well, you say whenever there's an area, there's the square root of the area. But yeah, that's true. But there are many, many different shapes with the same area. Not all of them are squares. Some of them are rectangles. They have the same area. Somehow the fundamental quantity is the area unit, not the length unit. It's what really always comes into important calculations. Yeah.
So the entropy in this case doesn't tell us anything about the internal structure at all.
No, that's just the point. The entropy is exactly all the internal structure that's being hidden and obscured by the fact that it's a black hole. It doesn't. The entropy, it does tell us something. It tells us how many degrees of freedom, how many elementary objects there are on the surface, but it doesn't tell us what they are. It doesn't tell us, right. Somebody asked me a specific question, let me answer it. They asked me about the luminosity of the black hole. All right. So we have the temperature. The temperature is, I'm going to now simplify the story, not simplify it so much, but I'm going to set h bar and c equal to 1. So the temperature then in units in which Planck's constant and the speed of light is equal to 1 is just 1 over mg. In fact, in Planck units, in units where h bar, c, and g are all equal to 1, those are common units, they're called Planck units, the temperature of the black hole is just 1 over it's just 1 over m. All right. Now, what's the luminosity of an object of temperature T? There's a formula, the Stefan-Boltzmann formula. Or is it called the Stefan-Boltzmann formula? Yeah. Yeah. And the answer is it's proportional to T to the 4th. T to the 4th. So apart from the numerical constants which appear, the luminosity, sorry, it's not 1 over T to the, not T to the 4th, it's T to the 4th times the area. Okay, T to the 4th times the area. The luminosity, I'll call it L, luminosity means the energy per unit time that's radiated from the object, is proportional to the area. Of course it's proportional to the area. The bigger the area at a given temperature, the more overall luminosity you have, times the temperature to the 4th. And there's a numerical constant called the Stefan-Boltzmann constant, which is made up out of h bar and other quantities. But this is the basic important thing. Now, the area is proportional to the square of the radius. The temperature is proportional to 1 over the radius. That means the area is proportional to 1 over the temperature squared. Right? Temperature is like 1 over the radius, and so the area, the radius squared, is like 1 over the temperature squared. And what we find out is that the luminosity is proportional to the square. Oh, I have something wrong here. Yeah, the square of the temperature. I think that's right. Yeah. Now, on the other hand, the temperature is also proportional to 1 over the mass. So this is 1 over the mass squared. The bigger the mass, the less the luminosity. The bigger the mass, the less the luminosity. Even though the area is much bigger, the temperature is so much smaller that it's the temperature effect which wins, and the bigger the black hole, the less the luminosity. You can use this to find out how long it takes a black hole to evaporate all its energy away. This is the rate at which it's radiating energy. Okay. 1 over m squared. You can use that to find out how long it takes for the black hole to lose all of its energy. As time goes on, the mass shrinks. As the mass shrinks, it becomes more and more luminous. And so there's a sort of runaway process. As it shrinks, as the mass increases, as the mass decreases, as it radiates, the mass decreases, the luminosity increases, and so as with time, it sheds its energy faster and faster, and finally just explodes in an explosion of energetic particles. So, but it takes a long time. Yeah.
I'm not sure this is a well-formulated question, but it seems you're saying that the Hawking radiation is not a quantum effect.
Oh, it is. Yeah, keep in mind, the temperature here has an h bar in the numerator. When you see an h bar in the numerator, you say that's a quantum effect. It would go away when h bar is equal to 0. Okay? The entropy would be infinite, but the temperature, which is the thing that controls the luminosity, the temperature contains the h bar in the numerator. Okay? If I neglected to say it, of course, this luminosity and this black body radiation that's being radiated is Hawking radiation. That is what Hawking radiation is. So, so the logic was you start by you start building the black hole bit by bit. You notice after a little calculation that every bit you throw in increases the area by the same universal amount. It's sort of as if the bits were impenetrable things that just accumulated on the horizon and blocked each other out so that the area has to grow to accommodate more bits, and the area grows with the number of bits. You discover that entropy grows with area. All right, that tells you that the entropy grows with mass in a certain way. If you know the relationship between mass and entropy, you can calculate the temperature, dE equals TdS. That gives you a temperature, and from the temperature you can calculate a luminosity, black body radiation, and the result is what is called Hawking radiation. No.
I'm kind of confused. On the one hand, I'm thinking nothing can escape from a black hole.
Well, who
On the
told you
other
that?
hand, we have radiation coming out of the black hole.
No, it doesn't come out of the black hole. It comes off the surface of the black hole. It never gets into the black hole from a point of view of somebody on the outside. But let's not get into the subtleties of inside. From the point of view of somebody outside the black hole, it takes an infinite amount of time to cross the horizon. That's just another way of saying for all purposes of measurements performed from the outside of the black hole, all things that fall into the black hole do not fall into the black hole. They accumulate on the surface of the black hole, or just above the surface. All right. Now, so it's, right, that's enough said. Yeah.
So is this a temperature then that would be in equilibrium with the heat bath, or?
Okay, that's an interesting question. That's an interesting question. The sun has a pretty well-defined temperature. You measure it pretty well, but it's not really in thermal equilibrium with its environment. Its environment is cold on the outside, and that's why it radiates away its energy. Okay? If it was in equilibrium, a thing in equilibrium won't radiate away its energy. It'll gain energy and lose energy at the same time. Now, there's a very, very peculiar thing, both about the sun, any system whose temperature is inverse to its energy has negative specific heat. The rate of change of energy with temperature is negative. Negative specific heat is very unstable. It's not impossible. Black holes and stars have negative specific heat, or negative heat capacity. The increase in energy makes the temperature lower. But it always means the system is unstable. If you try to put it, let's imagine we had a black hole in equilibrium with its environment. That would mean that its environment would have to have the same temperature as the black hole, and that would mean that it had the Hawking temperature, the environment. Okay? Now supposing accidentally the black hole emitted a little bit extra energy. You know, it's in equilibrium, so energy is going back and forth between it and the environment. But by fluctuation, by accident, it emits a little extra energy. What happens to it? Does it cool? Normally, if a system emits a little extra energy, it will cool relative to the environment, and then the energy will flow from the environment back to the cooler object. And so there's a sort of what do we call it? What? A regulating mechanism, which when an object in equilibrium gives off, by fluctuation, a little bit too much energy, it cools the object, and the result is heat flows back into it. What happens to the black hole? When it gives off a little bit of extra energy, its mass decreases, it gets hotter. And so it tries to give even more energy to the environment because it's now hotter than the environment. So there's a runaway. On the other hand, supposing the opposite happened, it absorbed a little bit of extra energy, what would happen to it? It would cool, and it would want to suck more energy out. So negative specific heat is always an unstable situation where, and black holes in that sense are unstable. If you try to put them in equilibrium with their environment, they will lead to runaway situations. So they can never be in thermal equilibrium with their environment. Yeah.
Yeah, if you take the delta for a bit of energy,
Which
each bit of energy is equal to an increase in area, then there has to be
each bit of entropy. Each
Yeah.
bit of entropy
But
is equal to a bit of area.
okay, and that's equivalent to the simplest particle falling into a photon.
The simplest particle.
The appropriate wavelength.
Right.
So
The longest possible wavelength that will get into the black hole.
So would that mean that there's the smallest possible black hole, which would be the area of the event horizon, would be the Planck area,
Exactly.
and that would be equivalent to
A black hole with less than one bit of information doesn't make much sense.
Okay, now if you take it the opposite, so associated with a bit of information is an area. If you take all the bits of information in the universe, would that be equal to the cosmic horizon? Is there any connection to that?
Yes. Yes. The number of bits of information in the universe is equal to the area of the cosmic horizon. 10 to the 120. It is a lot. And then a number of possible configurations of the universe is exponential of that. Right. Now, that entropy, the 10 to the 120, is much bigger than the entropy that you would count by looking at all the ordinary material in the universe. Most of it is stored out very close to the horizon of the universe. The ordinary bits of entropy in the form of stars and light. What's most of the entropy in the universe? Do you know? I mean, ordinary stuff that's visible. Okay, you might think that it was the background radiation because there are many, many more photons than there are anything else, but in fact, it's not true. The entropy is dominated by black holes. Yeah. There's something like about an entropy of 10 to the 90th or that order of magnitude in photons in the observable universe, but there are enough black holes at the centers of galaxies mostly that there's another factor of 10 to the 10th entropy in black holes. So most of the entropy, of the visible entropy, by visible entropy I mean the entropy and stuff that can be in principle seen, not associated with the horizon, but associated with more ordinary stuff, is about 10 to the 100, 10 to the 100 units of entropy. In addition, the horizon has another 10 to the cosmic horizon has another factor of 10 to the 10th bigger than that, 10 to the 120 altogether. And that's just from knowing how big the universe is and computing its area. So yeah, it's kind of interesting. Almost for every ordinary bit in the universe, there are 10 to the 10th bits stuck on the horizon of black holes. So almost everything in the universe is black hole or horizon information.
So any arguments about the old arguments maybe about the existence of black holes at the centers of galaxies? Is that, how does this apply to that? I mean, do we?
Well, I mean, no. I mean, we're counting the number of galaxies and assuming that each galaxy contains a black hole of approximately somewhere between 1 million and 1 billion mass black hole. That's what you find. You find that most of the entropy, ordinary entropy, in other words, the entropy of a galaxy is dominated by the entropy of the, in fact, the entropy of the vicinity of a galaxy, the space around a galaxy before you get to the next galaxy. It would be dominated by the black body the microwave stuff, but even that is overwhelmed by a factor of 10 to the 10th by the black hole at the center of the galaxy. So it's an interesting fact. Interesting fact for cocktail party. You can explain it to your friends. Yeah. Okay.
For more, please visit us at stanford.edu.